just wanted to make clear that you have heard about many different algorithms and concepts and whatever. So you can access those concepts at different levels as well. And so what we did previous week is there is an existing implementation. I've listed a PET NMR here, but obviously you have used FDK called filter back projection in CIL as well. So there is sort of an existing implementation that you could access as a black box, and you just run it on your data. These implementations obviously have many parameters. I think by doing some of the things this week, you will understand more of those parameters, but the implementations are also well, they rely on the underlying engine, and usually people have done a lot of work on them in some sense. Yes, you can choose to say, I'm just going to use an existing algorithm, but I'm going to take a bit out of it, which clearly you cannot do if you have a scanner console there, but with SIRF CIL you can do this. So for instance, show you an example later where you want to implement some filtering or anything like that during your iterations. Or maybe you say, well, I don't want to use an existing reconstruction algorithm, but I do have an objective function that I want to optimize, and I'm going to implement my own optimization algorithm, or maybe use one from SciPy or something like that. And finally, maybe you say, well, I don't really want to know about objective functions that have been implemented. I will just use, I take a paper, I see, oh, they're using some multiplication with the system matrix. I will use the same thing, and I just implement this algorithm myself. So these are all things that are possible because you have access to all the underlying components. So I'll show you very simple examples going actually from the bottom back to, so 4, 3, 2, 1 you have already done. So this is a very simple gradient descent implementation of the least squares objective function. So Andrew talked you through computing the gradient of this, and you see that there is a joint matrix here, so transpose and complex conjugate for MR. So how do we implement something like this in SIRF or CIL? Well, it's kind of obvious. The AX calculation is done by direct or forward. I have a slide on that in a minute. Then you subtract the data and you call the adjoint of your acquisition model, and you will be multiplying with the step size, and there you go, you have your gradient descent algorithm for least squares optimization. So that's, I believe, reasonably simple to do. So maybe you do have an objective function. So for instance, in PET, we have a way to make a Poisson log likelihood. If you give it some data in an acquisition model, there's lots of things then behind the scenes. And in CIL, you can create functions that do these things as well. And once you have that, you can just say gradient, as opposed to having to do the calculations that you have over here. You can rely on SIRF CIL to do all of this for you, and you don't have to worry about signs and all of those things. Now, I've written it here as a gradient ascent because I said see later, but actually I meant see earlier. Andrew has already talked to you that in PET, we're often doing maximization of a log likelihood plus a prior, while in other modalities, it's often something like least squares, which you want to minimize. So here it's an ascent algorithm. In other cases, you would want to do a descent algorithm. So, so that's also not too hard to do. A final way might be to say, well, I have an existing reconstruction algorithm that could be gradient set, could be conjugate gradient descent or ADMM or whatever, and you want to use just this to as a part of your own implementation. For instance, you just want to do one single update on your image and then do something to it. And I have an example here where you'd want to do a simple inter-iteration filter, or you could stick in a deep learning denoiser here if you wanted to. So, so these are the three levels that you can interact with, and you somehow have to make a choice when you want to tackle the problem that you are set. Yes. So just as a reminder, if you use the SIRF stir objective function, we'll be doing maximization. CIL generally set up to do minimization, so you want to be careful there. And we did encounter that last week as well, but I thought it might be useful to put this on a slide now and to give you a little bit of background. In PET, we often have a acquisition model that has a background term here, while in MR and CT, you generally don't. Now, you don't have to worry about this, but just as a note, that if you call forward or direct, they do exactly the same calculation. Yes, they their aliases, they do the same thing. If you want to do the adjoint operation of A, you call adjoint or backward. Again, they are exactly the same. However, if your acquisition model has a non-zero background in PET, and you would call adjoint, with any luck, it should throw an error and say, I'm sorry, the adjoint operation of this acquisition model is not defined. So that's a bit of math for you, which I'm not going to really explain to you what an adjoint operation is, but it's only defined for linear operators. And this is an affine operation, it's not a linear one. So in that case, if you want to do this, you do have to call backward. Or there is a way to get a linear acquisition model out of the normal one, but I'm not going to show that over here. So what you can remember from all of this is that backward and adjoint normally are the same, forward and direct are the same as well. Now, I thought many people ask me, well, okay, but if you want to do this backward operation in your algorithm, why is there no B term in here? Because the temptation is to think as this operation as an inverse or so. So you would be saying, I want to subtract B from the data first or something, and then multiply with this matrix. Now, Andrew already explained to you that we're actually not doing inverse operations. This is something else. This is a transpose or an adjoint. And I thought maybe it might be helpful to just show you in an example where I have a function of one element in my acquisition data. So just one element indexed I over here. Obviously, normally our objective functions are a sum over lots of elements, but in this case, it's just one of them to make the notation a little bit easier here. And so this is my full projection of the image into that element of the sinogram or the K-space. So I've just written that out here with an explicit sum. So if I now do the gradient operation with respect to one element of the image, like Andrew did, you will see, if you follow your chain rule, that you get this matrix here in front. And if you now need to do an operation where you need to sum over multiple elements of the image, you will be summing and therefore be doing transpose multiplications and so on. But the important bit is that in this operation, there is no B. I don't subtract with B because that's not how gradients work. So that's just maybe helpful for those of you who wonder why if I do an adjoint or backward operation, do I not subtract the data first? Okay, so Just continuing to give you some warning notes. Some algorithms need a linear model, so with this background term b equals 0. And so if you would give them one with a background, they should throw up an error. I'm not saying that they will in practice. I believe they do, but they should. So if you see that happening, it says, oh, I'm sorry, I'm not a linear model or something, then you know why. Just as another note is that what I've shown here and what Andrew has shown you, a lot of these equations are with something like a times x, maybe plus a background. Now, that means our forward model is linear or affine. However, in SIRF, we also have registration algorithms. But in that case, the forward model is not linear at all in terms of the deformation field or in terms of rotation parameters and so on. So that means a lot of the algorithms that we have are not applicable. And actually, at this point in time, we cannot return you the gradient with respect to deformation field yet. We have prototype implementations for it, but they're not yet merged into master. So you'll have to wait a little bit before you can write gradient descent for a registration algorithm. Okay, so as my summary is there are large similarities between all of these modalities, as I hope you've seen from Andrew's talk. And we've tried to make that explicit with this particular notebook, which is probably the one that you should start with. In our synergistic, it sits in the synergistic directory because that is the multiple modality type of examples. So do have a look there. It is listed in our list of notebooks as the first one. And it implements gradient descent for the 3 different modalities. But there are large similarities. On the other hand, some specific algorithms are needed for the type of data that you have. And obviously, we'll hear more about that in the next sessions.